Okay, I have started the recording. We will get started. So good morning, everyone. This is the in-lab workshop portion of RS103, radiated susceptibility to electric fields. And I will just state right up front, RS103 is an imperfect test, and I'm not going to sugarcoat it. You're going to see it warts and all, and I'm going to show you as much of how the sausage gets made as is practical in this session. And I will also freely admit that we're flying by the seat of our pants a little bit here, because we're going to, maybe that's not the best metaphor, but I'll go with it. But for the first part of the session here, I've got the camera in the lab to show you the general setup, but it being radiated susceptibility test to do it properly and not, anger our neighbors in the building here. We want to shut the door before we run an actual sweep. And we don't want to be in the lab while we're running an actual sweep radiating out of this antenna. So, we'll shut the doors, bring my laptop and the camera into the next room, into the control room where we actually run the sweep, and then you'll be able to see, we'll all be able to see what the field probe system is displaying. So there'll be a little bit of transition there where we're going to move everything into the other room. So just giving you a heads up there. I'm hearing a hot mic, so can you please mute if you're not asking a question? Yeah, thank you. Okay, so let's get rolling here. The centerpiece, several centerpieces, but the main item of interest for an RS test is the antenna. I'm just taking my badge holder off, and it's going to get in my way. So our test antenna is sitting right here. This is the ETS Lindgren 3117, the test we use for RS above 1 gigahertz. And this is the only one that I'm going to actually demonstrate in the interest of time, right? But I'm going to show you the charts that I showed from last week, just a handful of them to refresh your memory on the properties of interest of this antenna. But just to go over the general setup here, the antenna is sitting on a tripod, and this is a small antenna, so you don't need a really a huge tripod. In a second, I can show you the large DRG that we use from 200 meg to 1 gig is sitting out in the hallway. That's much bigger. That antenna is about yay by yay. So it needs a much more robust stand to put it on. So you just have to gauge that in your own lab what kind of stand you need for each antenna. And then of course you need a cable to get you from your drive amplifier. The drive amplifiers are in the next room. I'll show you those when we move over there. And the cable will have some loss. And if we get to it, I can have the guys pull up the loss curve for this cable. But we can generally ignore loss up to, well, through the Bicon range. Bicon's right over there. I'll show you that here. Well, I'll show you in just a moment. The Bicon goes from 30 to 200 meg. We still load up cable loss numbers for that, but you're generally looking at maybe a dB up at 200 megahertz, but it increases with frequency. So cable loss is something you have to take into account in these higher frequency ranges, certainly above a gig. So we have the same EUT. I'm not actually even going to bother powering up the EUT for this test, because to really do it properly, you'd want your monitoring equipment in the other room. You don't want to be in here. You don't want any of your monitoring equipment to be in the same room while you're irradiating everything, because then you don't know, you don't have any way really of telling whether it's the EUT or whether your support equipment that's exhibiting a susceptibility. So we're not equipped to do that today. So that's just not going to be part of the demonstration. It's just going to be the mechanics of applying the desired field. So the antenna is what applies the desired field. to the test setup. So the EUT we generally think of as the box. It's the power converter that we've been using, but again, it's the EUT plus cables. The EUT we generally think of as the box, but really the EUT consists of all the cables connecting to the box. So if you recall from Mill Standard 461G, that the 3 dB beam width of the antenna must encompass the first 35 centimeters of cables from 200 megahertz to 1 gigahertz. Above 1 gigahertz, it only needs to cover the first 7 centimeters of cables coming off of the EUT. And that is because I was addressing a question about this last week, that the mill standard doesn't explicitly say this, but I'm certain that it must be that at 1 gigahertz, the wavelength is, I believe it's 7.5 centimeters. I'm sorry, wavelength is 30 centimeters. A quarter wavelength is 7.5 centimeters. So 7 centimeters basically gets you about a quarter of a wavelength at the lowest frequency of interest. And as the frequency goes up, wavelength goes down, then you're encompassing a larger fraction of a wavelength as the frequency increases. So it's to get you about a quarter of a wavelength at the smallest wavelength of interest, or I'm sorry, the largest wavelength of interest. Okay. So so the antenna is what gives you the illumination of the test article, but you want some way of knowing what level that you are applying. So that's where your field probe comes in. And I'll go ahead and take the camera off. So the field probe, everyone can see this. This is what, as the name suggests, it is detecting the electric field that's being applied, and giving you that feedback of what level you are actually providing. And it's a 3-axis probe. You can see there's an X on top here, and a Y, and then a Z on the other side here. So you can display each of the 3 axes separately, or you can display it as an RSS sum. And then we'll have a look at that when we go into the next room. I'll talk about the placement of this probe here in just a second, but I'll show you a couple of the things that I mentioned here. Out in the hallway, you can see that. My apologies that the cable isn't any longer than this. But you can see the large DRG horn out in the hallway there. And because it's big and heavy, it needs a big and robust stand for it. Where this 3117 is much smaller and lighter, a more modest stand is sufficient. The biconical antenna is sitting right over there, just for show and tell. We're not going to hook it up, and that's what we use from 30 to 200 megahertz. In the corner here, we have the amplifiers that we use for much higher frequencies, from 18 to 40 gigahertz. We don't use these terribly often. We'll get a little bit closer here. Yeah, so the one on the right is from 18 to 26.5 gigahertz. Then the one on the left is 26.5 to 40 gigahertz. We're not going to hook these up today either, but we have used these from time to time when there is a specific need to test above 18 gigahertz. And as I mentioned, cable loss gets to be more and more pronounced as you go up in frequency. Well, you see that there's a waveguide port on the front of each of these that the test antenna mounts directly to that. So because cable loss is so significant above 18 gigahertz, excuse me, they eliminate or significantly minimize loss by just mounting the antenna directly to the front of the amplifier. So that's about as much show and tell. Now, you may ask, because I just said above 1 gigahertz, the mill standard says thou shalt have, thou shalt illuminate at least 7 centimeters of cable. Move my meter stick here. 7 centimeters of cable from the EUT, from the box. So 7 centimeters goes out to about there. It's only about 3 inches. So why did I put the field probe way out here? That's a very good question. I'm glad you asked. And for that, I will, let's go back to these charts from last week, and I will explain that, because this is an important thing that is central to what we're talking about here and what I would like everyone to take with you when you plan for a test like this. So share my screen. All right, can everyone see the charts?
Yes.
Okay.
Yep.
Let's go back to this one. And hold on. Trying to go to slideshow mode, and it is not cooperating. Hold on.
Got one orange.
There we go. Okay. So this is the this is the half power beam width, gain, and VSWR, voltage standing wave ratio curves from the data sheet for the 3117. Main ones of interest for this discussion are going to be the half power beam width and the gain. But you can see that the dark blue curve is the H plane, and the maroon curve is the E plane. Okay, so, well, what does that mean? Well, I'll put the camera on the antenna here again in just a second, but from the picture here, the E plane is in the direction of the elements. So here are your elements, your conductive elements. And so the E plane is in that direction, and the H plane is in this direction. So you are still, I mean, RS103 is all about electric field, right? I mean, so if you have an electric field, you have a magnetic field too, but the H plane just means the direction orthogonal to the direction of the elements. And I'll show you a close up of the antenna itself here in just a second. So, but you need to consider both, right? So your worst case is that the E plane is about 50 degrees at 2 gigahertz. So from 1 to 2 gigahertz, which is what we're going to do here, at least for starters. We may only do that in the interest of time. Oh, thank you. And actually the next chart is what illustrates that. Here at Goddard, and this is where, you know, this is all your mileage may vary, right? None of this is cookie cutter, thou shalt do it this way, or any of that. This is just, you know, giving you the thought process for how you approach this within the capabilities and constraints of your own lab. So here at Goddard, the way the amplifier rack that we have for running RS103 above 1 gigahertz is shown here. It's what we're going to look at in the next room here. But it's divided into these frequency ranges as shown here. Generally factors of 2, 1 to 2, 2 to 4, 4 to 8, and then 8, it just goes 8 all the way up to 18. Okay, so each amplifier must be warmed up and connected individually. And actually for this demonstration, these are traveling wave tube amplifiers, so tweeters, and they take a very long time to warm up and such. So from 1 to 2 gigahertz, we have a solid state amplifier that we're going to use. I believe it actually goes up to 2.5 gig, right? Yeah. But that's the one we'll use here for this demonstration. But given that for our configuration here, if you need to change out the amplifier for each frequency range, then you don't necessarily have to use the same antenna position in each or set of antenna positions in each frequency range, right? You can make these adjustments according to spot size. And so there's no need to maintain constant antenna positions over the entire frequency range. So if you've got this sort of arrangement with your amplifier configuration, I think it's fairly typical, but not necessarily universal. But the frequency breaks may be a little different. But you can use this to your advantage when we go back to look at the beam width curves for this particular antenna. You see that we start with a pretty generous beam width. In fact, at the low end here, so 1 to 2 gigahertz is just this very small range right in here. The E plane is clearly the worst case. The H plane is very wide, but we want to basically look at the H plane as the worst case. So 50 degrees at 2 gigahertz, that's our worst case, right? In that lower frequency range. 2 to 4, it's a bit more generous, right? We go up to almost 60 degrees, but then it goes down as we go up in frequency. So if you want to use a large number of antenna positions to get decent coverage, because your worst case is actually the H plane here going down to 22 degrees at 18 gigahertz approximately. If you use that very small spot size to determine how, if you need four antenna positions in that higher frequency range, you can do that, but there's no reason to do that in these lower frequency ranges where you have a much wider spot size. Okay, so let's look at some specific numbers here. Hold on. There we go. Calculator. Okay, so just looking at this specific example here, 50 degrees at 2 gigahertz, that's plus and minus 25 degrees off of bore site. Forget you saw that because that's the answer. But so if it's 50 degrees end to end of our beam width, 25 degrees off of bore site, so we take the tangent 25 degrees, and we're starting with a distance from our antenna to the UT of 1 meter. We're not tied to that, but that is the default that I'm going to use here. Well, the tangent of 25 degrees is 0.46. Well, and related to 1 meter, if 1 meter is my cosine side of that triangle, that tells me that the radius of my beam is 46 centimeters, 0.46 meters. So the total, the diameter of my spot size is twice that. So, whatever, 93-ish centimeters. So almost a meter. So that's a pretty good spot size. And that's more than adequate to cover this small EUT and 7 centimeters of cable on either side. But the edge of my 3 dB beam width that we just calculated here is 46 centimeters off of the bore site line. So I certainly could put my field probe at the 7 centimeter mark, but I'm choosing to put it at the edge of my 3 dB beam width so that I know that basically everything inside that 3 dB beam width will be at least that level. Will it be at least my desired level? So I'm going to level at that point, 46 centimeters from the UT at our desired level, whatever that is. We'll probably try a couple of different levels, 5 volts per meter, 10 volts per meter, whatever it is. But as I said, RS103 is an imperfect test. You're not going to bathe the entire EUT in a constant electric field. That's not possible. You're not in the far field by any stretch. So, but if you put the field probe at near the edge of the 3 dB beam width of your antenna in a given frequency range, then you know that what the field probe is sensing at that location should be approximately the minimum, and that everything inside that 3 dB cone should be at least that. Okay. And so I'll go back to the camera here to show you a little more of the specifics of what we're talking about. So can you see the view in the lab again?
Yep.
Okay, so let's grab the camera and let me not trip over my power cord. Okay, so you can see the antenna here. So this is in horizontal polarization. That's Walt, by the way. Walt's on TV. You're okay. So here's this is horizontal polarization, right? It's the direction of the elements. And so this is your E plane. Okay, and then the H plane is in this direction. So a couple of things to think about here, and you got to take that into account, whether it's in vertical or horizontal polarization. Well, per the mill standard, the antenna is supposed to be 120 centimeters up off the floor. Our ground plane is, well, the mill standard says between 80 and 90 centimeters. We split the difference and it's right around 85, might be 86, but call it 85. That means your distance from bore site in this direction, your bore site's right about here, then the edge of the EUT or the ground plane is about 35 centimeters off of bore site in the vertical direction. So you have to take that into account, that to make sure that we tend to think of just in this direction, in the horizontal direction. Are we getting enough of the cables within the 3 dB beam width and all that good stuff? But you also have to take into account in the vertical direction, is that 35 centimeters going to be sufficient? Or is your 3 dB beam width going to be sufficient to make sure that you are indeed within that 3 dB beam width? Now we just calculated that in this frequency range, the worst case for the E plane, which is in this direction, is 46 centimeters. And I don't remember what exactly the H plane was, but it was much higher than that. And if we just use 46 centimeters as our worst case, then we know we're good. Okay, because 35 centimeters, we know that the edge of the beam is a good 11 centimeters further down. We're good there. So you got to keep all that stuff in mind when you're looking at these spot sizes. You got to look at both E plane and H plane. We tend to, I've been guilty of it. I tend to look at E plane only because, hey, we're applying an electric field, right? So you look at E plane. You got to look at H plane too, to make sure that your entire, that you're getting everything you want in the 3 dB beam width of the antenna in both directions. That certainly simplifies things when you use the worst case between E plane and H plane and think of the beam as a circle, or cone, I guess, but the spot size as a circle. But nothing's stopping you from really scrutinizing both E plane and H plane, thinking of it as an ellipse if that works to your advantage, right? If you're in, here we're in horizontal polarization, and if you've got a nice wide E plane but a narrower H plane, well, sure, in horizontal polarization you can use one set of antenna positions, or maybe just one antenna position to give you all the coverage you need. And then when you go to vertical, then you might need an additional antenna position or what have you. So again, it's not cookie cutter. It's not thou shalt do it this way or that way, but it's to use the information at your disposal and use the information in the data sheets for the antennas you're using to make these informed decisions about what number of antenna positions you need to get the adequate coverage for your test setup. So getting back to that 46 centimeter number, that's this, and here I'm going to move the ruler to the center of the box. Well, I put the field probe right around 46 centimeters from that center point, because I did that calculation just before we started. So I want to make sure that I'm getting the desired field strength where I've put the probe, and that I know that the center of the test setup should be getting, well, theoretically 3 dB higher than that. But again, it's imperfect. It's not important whether it's getting exactly 3 dB higher than that, but all we're gonna know is what the probe is seeing. Now, sometimes we'll put multiple probes up, and you might put a second probe over on the other side, and you can do things like average them. That sort of thing takes a little bit of extra time, but you can do that, right? Right now, we just have the single probe set up, just for the purposes of this demonstration. But we have done, with multiple probes, and we might do, like just, at each frequency, we'll look at the maximum of what the different probes see, or maybe take an average. There are different things that you can do to meet your needs. So,
We have a show and tell part of the microwave.
Greg has a show and tell. Go ahead, Greg.
This is the 18 to 26 gigahertz horn. That's for the high frequency, the amplifiers John showed you earlier. They attach through these waveguide and has like little tiny screws. So it's a lot of setup.
You want to take it over there?
Yeah.
So. Hang on. I need to turn my computer to be able to see what I'm showing you. Okay.
Yeah. So they attach right here. They make, and then we can, to change the polarization, we take out the waveguide. But yeah, that's the horn that's used for the 18 to 26, and there's another one for 26 to 40 gigahertz. But yeah, it goes right here. So it's a very small area that we can beam. So we have to have more antenna positions for that, unless you can make it the level of the probe.
Now those are pretty high gain horns. I don't know exactly what the gain of that one is.
Yeah, I mean that's.
No, there you go. And then but we'll say that one's for 18 gig, if the cavity for that one.
Yeah, that's for this one.
So the higher frequency is a bit smaller.
A bit smaller, yes.
So. Okay,
Yeah.
so one other thing I'm gonna mention, I need to go back to the charts, the boring charts and lecture bit. But, again, need to know what you're doing before you hook up the test equipment, especially, several 100-watt amplifiers. Let me go back to the charts. So one other thing I wanted to point out here is, and I went through this last week, but just to review, yeah, here we go. So transmitted power versus radiated electric field. Again, this is to just give you a starting point. I'm not taking into account things like cable loss and room resonances and stuff like that. But just as a starting point, it's a very simple calculation to relate transmitted power versus radiated electric field. You have these two equations to start with, and I always go back to this because this is stuff I can remember. I've never been particularly good at memorizing. So I don't just like to memorize an equation. I need to know where it comes from. And if it's like a 3-step derivation, I know I can always get back to it. So power density of a plane wave of electric field intensity E in vacuum or air is an approximation, right? We know we're not in the far field by any stretch here with RS103, but it's a decent approximation as a starting point. But the power density is the square of the electric field divided by the wave impedance, which for a plane wave in air is 377 ohms or 120 pi. 120 pi is useful to use here in this situation because it will cancel out. But so then the power density at a distance r from a transmitting antenna with gain G, again, this is a far field approximation, but if it's an isotropic source, then it's just that transmitted power divided by the surface area of a sphere of radius r, 4 pi r squared. And so the definition of gain G is just the ratio of the actual power density to the power density you would get from an isotropic source transmitting that same power. So the power density is just that isotropic power times the gain. Okay. So now you have these two expressions for power density. You set them equal to each other. and then you can just solve in one case for transmitted power as a function of electric field, or rearrange terms to get electric field intensity as a function of transmitted power. Okay, so just looking at a couple of examples, if you want to get a field intensity of 20 volts per meter with your antenna at a distance of 1 meter, and a gain of 3, which is in one of the examples from an earlier slide. We can go back and look at that in a moment. But for this particular example, you would need almost 4.5 watts. Again, neglecting cable loss or room resonances or any of that. And so you would ideally want an amplifier in the range of 10 to 20 watts, right? You want a little bit of headroom above the power you actually need, but not so much additional headroom that if you, for whatever reason, accidentally go to full power, that you're blasting your EUT with, 100 times more power than you need, right? And then if we move the antenna back to 3 meters, well, since the power is going to go with the square of R with R squared, that will be almost a factor of 10. It'll be a factor of 9, but you'll need about 40 watts to get that power. So there you'd want an amplifier of maybe 1 to 200 watts. Again, you're not including cable loss, room resonances, or any of that. This is meant only as a starting point. But it at least gets you in the ballpark of what kind of power do you realistically need, and then compare that to the in fact, I believe that's the next slide.
Hey, John.
Yes. Hey, Dipendra, what's up?
So I know how to apply for that cable loss, but how about the room resonance? How do we account for that during the test?
Well, that's a difficult thing to predict. So when we fire up the amplifier and actually start applying a level, we'll probably see some of that. Like you'll see the power, because when we run the sweep, we'll be monitoring the electric field that the probe is sensing, but we'll also be monitoring the amplifier power. So when you see the amplifier power going up significantly to maintain a given field level, you're probably hitting a room resonance. And that's just a very difficult thing to predict. And if you do find one, well, it's not really if, it's basically a question of when. I guess one of the things we do is just shift the field probe a little bit in that frequency range. If it really becomes a problem, because if you just run up against the limits of your amplifier power and you just can't get to that level, we'll generally just skip over that frequency range until we can reach the level again. Then we'll come back and revisit the problematic frequency range, and maybe just shift the probe a little bit, because if it truly is a room resonance, then it's that particular location in the room. And in this frequency range, we should really only have to shift the probe by a few centimeters to get out of that null. So yeah, it's a difficult thing to predict, and it's not really, I don't think we generally really do. We run the sweep, and then if we see the power level go up, yeah, but we'll see that here in just a minute when we hook things up.
Yeah, thank you.
So if we go back to, I want to go back to this plot here, or this page. So we've talked a good bit about the beam widths, but then the gain curves are very useful. Some of these antennas actually, the 3117 doesn't do this, but other antennas will actually give you a graph of forward power versus electric field at some given distance. I think the Bicon does that. So that's very handy if they give that to you directly. But if not, you can back that out using the equations I just gave you from these gain curves. So again, your mileage may vary, but in the Goddard scheme of things, where we have, with the range of frequency ranges our amplifiers work in, from 1 to 2 gigahertz, your minimum gain is 0 dBi or unity numeric. 2 to 4, minimum gain is 5 dBi or about 3 numeric. 4 to 8 is about 8 dBi or 6.3 numeric. Always pay attention to the units here, because if they're talking gain, they should be giving it to you in dBi, but sometimes they might give it to you numeric, so you just got to pay attention to that. And the numeric value is the one you want to plug into that equation, right? The equations on the other slide, that G is a numeric quantity. So you just always got to pay attention to when you're using a dB value or a numeric quantity. And then above 8 gigahertz, the gain is the minimum gain is about 12 dBi or about almost 16 numeric. So that what that tells you is that among other things, as the beam width goes down, as frequency goes up, well, the gain is also going up. I mean, that's the nature of things, right? Generally speaking, increased gain means lower beam width. Now, gain also includes, efficiency or inefficiency terms, right? So so sometimes you'll see a gain. You may see like the Bicon has a very high beam width at low frequencies, but the gain is very low. And it's because because of the inefficiencies. But generally speaking, when gain goes up, the beam width goes down. But as the beam width goes down, here, you have higher gain to work with. So if you need to move the antenna back to get, if you move the antenna back from 1 meters to 2 meters, then your spot size doubles. You move it back to 3 meters, it'll triple. But then the power that you need to get that same electric field goes up with the square of the distance. So you need 4 times the power at 2 meters and 9 times the power at 3 meters. But if your gain is going up, with frequency, that will somewhat offset how much additional power you may need. Maybe not entirely, but again, this is all the stuff to look at as you're determining antenna positions and things like that. Know that you're not tied to a 1 meter distance for antenna placement. You can move it further back to get a bigger spot size, but you do need more amplifier power to get a given electric field. Because our spot size or our beam width is so generous, in this lower frequency range, I have just put the antenna at a distance of 1 meter. That's more than sufficient to get the coverage we need. So all it would really accomplish, if we move the antenna back, that's all well and good. We'd illuminate more of the EUT, but we'd need more amplifier power, and there's no real driving need to do that. You move the antenna back as the beam width is shrinking, and then you basically you're scaling the spot size as you move the antenna back, and as the gain is increasing, it somewhat offsets how much additional power you need. Okay. Anybody have any questions before we shift and go into the next room and actually start running some stuff? Okay, well, I guess everyone's chomping at the bit to run some stuff. So now to do this properly, you would move certainly all of the metal objects out of the room. We're not going to bother with that in the interest of time. But like that Vicon antenna right there, I suppose we could put that out in the hallway, but like the Vicon, any of this stuff, really, you want to clear the room as much as possible when you're doing these, doing any radiated testing. The other stuff we're just gonna leave in here. I don't think it's gonna make that much difference. I mean, we're just showing the basic mechanics of how you run these tests. Probably will affect room resonances somewhat, but at this point we're we're gonna shift into the next room, and so stand by as we do all of that. I'm hoping I don't lose the network connection while we do that.
So, we're gonna close the door. Okay.
Let me go into the next room and make sure I keep the internet connection before you do that.
Yeah.
We're gonna make before break.
You grab the camera with you?
Yeah, please. Oh.
We will travel.
All right, so Greg is carrying you all into the next room with me, so. Do we have a hardline connection in
Yeah,
here?
we do.
Okay, where is it? I can just put this over here if need be.
Well, you wanna put like it on it, you can put it probably there. That's fine. That thing.
Okay, I'm gonna want to be able to show the
Yeah.
probe display here. All right, then we'll do that. Oh, okay, thank you.
Yes, you do.
Yeah,
That's on this.
all right, I'm gonna go to the hard line Ethernet connection. I'm hoping that doesn't disrupt things. Got them change it, right?
Hold on, let's just check this.
Okay, everyone's still there? Can you see and hear us?
Yep.
Yes.
Okay, great. All right, we're gonna close up the chamber doors and then we'll get moving. Okay, let me
Are you ready to?
well, let me just describe what we're seeing
It's
here.
gonna get noisy.
So yeah, these amplifiers are loud, so you may benefit from some of the filtering or noise cancellation or what have you, but this is the amplifier rack. I believe it's just the very same rack I showed in the chart. If not, I think you have two of these, right?
Well, no, this is it.
Okay.
This is the 1 to 18. 1 to
Okay.
2 to 4, 4 to 8, 8 to 18.
Right, and then this is the solid state one that we're gonna be using here today. So we have a directional coupler tapping off of the RF output. It's upside down, but it says 35 dB right there. So what's coming out of the directional coupler is 35 dB down from the level that's going on this cable going out to the antenna. And so that's what is being sensed by the power meter that then goes into the software. So they have to take that 35 dB attenuation into account.
Yes.
Right, but they monitor the power that is required at each frequency to get the desired field level. And this is the display unit for the field probes. And if you can quite see this, unfortunately, it's just kind of washing out the screen here. That's too bad because I really wanted to show you this number, but the without the amplifier being on at all, it's displaying 1.6 or 1.8?
1.6.
1.631 volts per meter. Oh, you can maybe almost make that out now. So, yeah, my
Yes,
apologies.
there.
There we go. Might be able to see it just a little bit. So about 1.6 volts per meter without doing anything. It's just what the field probe, whether that's the noise floor of the measurement system or whether that's actually the RF background in the room, I don't know. But what this tells you is that our default level of 2 volts per meter we generally apply for on orbit is very difficult to attain, and it's almost a non-test. So we sometimes just even if the requirement is 2 volts per meter, sometimes we just go up to 3 or even maybe 5 volts per meter, just to give us enough headroom over this noise floor or background to give us something we can comfortably and reliably level on. Because trying to level on 2 volts per meter when you got a noise floor background level of 1.6, it takes a bit longer to actually achieve level. It's non-trivial. So that gives you an idea of what you're dealing with just right from the get-go. One more thing, this is our signal generator right here. So yeah, you apply an RF level at each frequency, stepping according to the table I showed you in the charts last week. So we start at 1 gigahertz and we have 1% step sizes per GSFC. The mill standard is 0.25% step sizes. So, but this goes into the amplifier, and then the appropriate gain is applied because you need a lot more power than the signal generator can provide to actually drive the antenna, right? Generally these signal generators are, they used to be limited to 0 dBm. I think this one can go up to maybe 20 or even 30 dBm, but not much more than that. Probably not 30, maybe more like 13. 13 dBm is 1 volt. So, but whatever. Even if you can get a watt, 30 dBm is 1 watt. You need tens of watts or more to get some of the levels we're talking about. So signal generator, amplifier, and then the amplifier goes to the antenna, but goes through the directional coupler so that we monitor the power level that's going out. So there we are. I think Greg is chomping at the bit to turn this thing on, so let's do it. You hear it revving up.
That's not as bad as the TWTs. Yeah. Hopefully it can zoom. Sounds right.
All right. Good. Everyone hear the whirring? The TWTs are even louder than this. Now the solid state, it looks like it's got to initialize and all that stuff. I think that the TWTs, they have a digital display too, so there's probably some sort of microprocessor in there, but I don't think that takes long to initialize.
So one of the things is the light bulb.
Yeah, we have a light. Again, it's probably washing things out, but the light says caution, radio frequency, radiation hazard area, do not enter. So we turn that on when we're doing radio facility stuff. We clearly we don't need to turn that sign on for radiation emissions tests because the levels are significantly lower.
So no volts, that's good sign. So let's go 20 volts per meter.
Yeah.
Okay.
We'll start with 20 volts per meter. That's
well, you want to talk about the
okay.
And
All right, so we're gonna have to come over here. Well, why don't you describe what we're saying, Brad?
yeah, so you can see.
I'll turn this.
Yes.
It's kind of washed out, isn't it? Yeah, it's a little better when you bring it closer.
Okay.
Okay.
So on this side, right side, you see the level. We are set for 20 volts per meter limit. We have the frequency is 1 to 2 gigahertz. And on this side, we have the same frequency, 1 to 2 gigahertz. We limit our power in this case to 14 volts, 14 dBm. And we basically that's how it's not going to go any higher than that. So that's one way to protect it.
That 14 dBm after the 35 dB directional coupler.
Actually, based on the calculation, we could probably go as high as 19.
Okay.
But we went with 14. I gotta take this.
All right, Greg had to take a call, but if we go back to our equation for calculating this, here, I'll pull the charts up again. All right, so our gain, our worst case gain for this horn in the 1 to 2 gigahertz range is unity numeric, 0 dBi unity numeric. All right, so if we go to our equation, the power required, we want to determine what is the power we need to get 20 volts per meter at a distance of 1 meter.
Okay.
Oh, I meant to point this out as I was walking through this, but the 120 pi is useful here instead of 377 ohms because you have 120 pi on one side and 4 pi on the other. Well, so the pi's cancel, and then the 120 divided by 4 is what gives you 30. So if I just, first time I saw these equations, when somebody just gave them to me, like, where did the 30 come from? Well, when you know that it's 120 pi divided by 4 pi, then, okay, then it makes sense, and then you remember it. Anyway, so if we look at use this equation, we want to get 20 volts per meter squared, and then we're at 1 meter, so that's just 1 squared. So we'll do that anyway, just for completeness. All right. Then divided by 30, and then our gain is 1, so we just leave that. So this tells us we need something on the order of 13 watts. Okay. So 13 watts, well, so 10 watts is about 40 dBm. All right, so, and Greg was saying that right at the moment, he's got the power limit set for 14.5 dBm. That's at the output of the directional coupler with 35 dB of attenuation.
Right.
Right. So if it's 14.5 dBm plus 35 dB, let's just call that 15 dBm plus 35. That's about 50 dBm.
Yeah. And the max
So
is 250 watts, is
53.
54 dBm.
okay. So that's not a bad choice, right? The power, the amplifier that we have is we don't necessarily need to look at providing any attenuation, right? For 20 volts per meter. If we're going down to 2 volts per meter, while we need 100th of the power, we might want to consider putting an attenuator on there. The other thing with the attenuation, these amplifiers, these RF amplifiers, generally prefer being driven near full scale, right? If it's a 250 watt amplifier and you're trying to put a watt out of it, they're a bit more fussy. I think I think you'll get a little more noise, and it may be a little less reliable to get the desired level out of it. They're meant to be driving something pretty close to full scale. So if you want 2 watts out of a 200 watt amplifier, then putting a 20 dB attenuator in there, all right, with some headroom, so maybe call it a 10 dB attenuator, allows you to drive the amplifier up to near full capacity, so where it's more reliable and stable, and then you get the protection you need so that the minimum level you can apply your hardware is reasonable. So, okay, so Greg's back.
Yeah.
Here you can get back in the driver's seat. All right, I'm gonna go back to the camera. You bring it closer. So still working out the kinks of carrying this camera around and stuff. So appreciate your patience. Yeah, I don't know. I hope you can see the display.
Either you put the driver in or the camera.
What's
Okay,
that?
so.
It's either we
thing
fit the
is-
driver in or the camera.
So the clicking you might be hearing, I think
We're
it's a signal
going up
generator.
to 20 volts.
Yeah, there we go.
It is the
Okay.
generator, has really clicking.
Yeah. Yeah,
So
yeah,
we're
yeah.
stepped out. So we're sweeping right now.
Bring one.
Okay. So the display unit over here that's off camera, it is showing that we're getting up to 20 volts per meter. Like I said last week,
Okay, that's not.
you
Okay.
you drop the level after you come up to level at a given frequency, you drop the level by, I'm not sure what you have it set for, dropping it like 12 dB. But you drop the level, step up to the next frequency, come up to level, and then turn on modulation and dwell for
1 second.
1
1
second,
second.
and then turn off modulation, drop level, go up to the next frequency. Now, it might be kind of hard to see on the screen here, but on the right, is the field intensity.
Yes.
This is the electric field intensity.
Trying to get to 20 volts.
Yeah.
Stay basically on 20 volts per meter.
Now, what is the tolerance that you've set up there? Like -0 to +1 dB or so?
It's pretty low.
Okay.
We try to minimize that error.
So if you set that tolerance to something ridiculously tight, like -0 dB and +0.01 dB, it'll take a very long time to level at each frequency, and it will make the test go longer. And there's no need for that. We're not looking for 0.01 dB problems here. So we generally set it for -0 dB and plus maybe 1 or 2 dB. So just when you relax that tolerance, you can level much more quickly and just keep the test moving. Now on the left is the power. So what's the difference between those two lines?
Actually, it was two different groups. No, one is forward power. The top one is the forward power measurement, and the bottom one is the SIGGEN output.
Okay,
So we track both of them, and obviously we don't want any of them to exceed the limit.
so I don't know how easy that is to see, but yeah, the top line on the left, the dark blue line, that's the output of that's what the power meter is reading.
Power meter, yeah.
That's the 35 dB below the actual level going to the antenna. And then the green line is the signal generator output, and you would expect those to track. They are. And the dashed line is the power limit. Now that's software configurable, right?
Yeah.
So one of the things you see that we're getting kind of close to it. We got pretty close to it here at wherever that is, maybe 1.2, 1.3 gigahertz. But we didn't quite hit it. That's the sort of thing that's going to happen at a resonance. Depending on how sharp the resonance is, I mean, that power level could shoot up pretty quickly. And then you'll just hit the power limit and stop. Right, and by the way, this is, I was going to say this is EMC 32. That's not right.
No, this is tile.
This is tile, right? EMC 32 is what we use for emissions measurements. But this is tile, it's been around forever.
Yeah.
Number of people use this. You might use it in your EMI lab. I have no idea, but if you don't use tile, it's something equivalent. I mean, everything does something like this, where you're monitoring what the field probe is saying, and then monitoring the power level that you're applying. So, so far this is reasonably well behaved. The amplifier itself is also displaying forward power. It's going up to about 54. It's going 60 watts. So yeah, 70. That one went up to about 75 watts. Oh, now it's okay. It looks like we might be hitting a resonance. It went up to about 176 watts.
Yeah.
And we can see it turning up.
Right. That,
Okay.
that's the sign of resonance.
Yeah,
We didn't quite get to that level. Something was
Yeah.
reflecting. And it got limited by the power.
Yeah. Can you see the dip in the field plot? We didn't quite get the 20 volt per meter level at that frequency. So that's the sort of thing, and I guess it's set in the software that if you're not able to reach level out after so many tries, it just moves on.
Yeah.
Something like that.
Right, you have to either repeat it or just.
Right.
Note it that.
Because sometimes if you don't set it to do that, it may just stop. It may just say couldn't level, and then it prompts you, do you want to continue or what have you. But that's most likely some kind of a resonance. Now that's not it's not too severe. Sometimes we hit a resonance where
Yeah.
the maximum level is way down here somewhere, and we are very much at the power limit, and then we have to take some measures like move the probe, or that's the main thing. Go in and just reposition the probe. Okay, the sweep is done.
Yeah. That's it. That's this complete.
And like what level did we hit? 17.6, I think it is. 17.5.
Yeah, but
So that would be a judgment call, like what you would do about that. I mean, if you didn't reach the level at one point, remember, it's just what did the field probe see? And what the unit under test, what the box may have seen could be something very different. So that's kind of a judgment call. I think in some cases we might have just said, this is fine, and we move on. But for completeness, for thoroughness, we probably would go back to that frequency or just a small range around it, move the probe somewhat, and just from an engineering standpoint, I in some cases I might be inclined to say, yeah, we're fine, let's just move on. But going beyond that, just thinking in terms of 6 months, a year, or 5 years from now, somebody looking at the test report, hey, what happened there? It can just significantly reduce or hopefully eliminate the swirl that can happen if somebody sees that little dip below 20 volts per meter and wants you to spend half a day explaining to them why it was okay to keep testing. Sometimes just go back and do it, just so you have a complete record that you hit 20 volts per meter at every frequency. And if you try to explain to them that the field probe is 40 centimeters away from the EUT and blah blah blah, that good luck. Because the person asking that question is probably not one who's really gonna be savvy about that sort of thing. So sometimes just go beyond the technical explanation and just do that little bit again, get a complete set of data, just so that you avoid having to explain yourself, at some point down the road. So that's the general idea. Gradient susceptibility. I think that's really about as much as we were going to show today. I'll tell maybe we can turn the amplifier up or put it on standby.
it's already on standby.
No. Okay.
It's not. It's
All right. There we go.
much better.
So Greg shut off the amplifier. Can everyone still hear me?
Yes.
Okay.
Yep.
So I'll just describe this. I was thinking about going back into the other room, but we made everyone dizzy carrying them into this room, but
This cable's pretty long.
that's okay. There was just a war story I'll tell. I was supporting a test at another nameless facility about 10 years ago, and we were actually using the Bicon. This is just another example of the trials and tribulations of using the Bicon. So as I've mentioned, we generally, unless you've got receivers, no, here, let me turn the camera around. To make it more like a fireside chat, like I like these things to be. So there we go. Here's our fireside chat. You know, we have this, you know, our fireplace back in the corner there. So but so I said I think this was 10 about 10 years ago, something like that, maybe 8 or 9 years ago, supporting a test at another facility. And so we're using the Bicon. We generally don't like using the Bicon, or there's no need to use the Bicon if you don't have radio receivers or transmitters operating below 200 megahertz. You know, our common mode conducted emissions and susceptibility tests that I've talked about in other sessions are much better ways of addressing cable-to-cable crosstalk than radiated emissions or susceptibility tests. But be that as it may, we applied these, you know, we applied RE and RS across the whole frequency range. So we're doing RS, we're using the Bicon in the 30 to 200 megahertz range, and each of these amplifiers, kind of unfortunate we turned it off, but each of these amplifiers will display forward power and reverse power. So remember, the antenna is a passive unit, right? The amplifier is the active portion. So any of these antennas can be both transmit and receive. You know, many of these antennas we do use for both. Sometimes they're optimized for one or the other, but any antenna can be used for either one. So when you're transmitting out of one of these antennas, any energy that comes back to it is just going to go back on the cable and back to the amplifier. But that's actually the whole point of this. So when we were doing this test, we were doing an RS test with the biconical antenna. The amplifier was going nuts. The reverse power indicator was in some frequency range was going through the roof. I don't remember if it was actually shutting down the amplifier or putting it into standby or whatever, but we were standing in front of the equivalent rack of amplifiers, and we saw that reverse power number go to, you know, several hundred watts. I think it might have been a 500 watt amplifier, but whatever it was, maybe it's 200 watts, but it was going pretty much up to the rail when we were trying to apply maybe 10 or 20 watts. So like, well, what's going on here? Well, the biconical antenna, just picturing the two wings of the bow tie antenna pointing right straight at the EUT, parallel to the wall behind it. Now, I think this particular facility may not have had ferrite tiles. The ferrite tiles behind the conical anechoic material is really what's going to be effective at low frequencies. The conical anechoic material tends to be more effective. It's more effective at higher frequencies. And I think it really kicks in maybe at the higher end of the biconical range or maybe above, like a few hundred megahertz. So I think this facility did not have ferrite tiles behind the cones. So there's basically effectively no absorption. So you're pointing the bicon at essentially a metal wall. You know, your anechoic material is doing you no good. So you've got this very, reflective metal surface behind the anechoic material. All that energy is coming right back into the bicon, going on the cable, going right back into the amplifier. And so what we did to deal with that was we just rotated the biconical antenna just a bit so its axis was not quite parallel to the wall. So then any reflected energy, you're not stopping the reflected energy, but you're just redirecting it so that it's going away from the antenna, right? So not nearly as much of that reflected energy was coming back into the antenna and causing problems. So that's just another fun thing that can happen with RS103 that, you just got to pay attention to that because it may well happen. Even in this situation, we've got the DRG is pointed directly at the back wall, but we're going above a gigahertz here. The anechoic material is a bit more effective, and I don't think I saw the reverse power indicator really coming up.
Not much, really, if any.
Yeah, so,
Didn't need it.
so, you know, the higher up you go in frequency, the less likely that is. The wavelengths are going down, so constructive, destructive interference is just less likely. It's just kind of more diffuse or diluted, if you will. But the bicon range, as I pointed out last week, 30 to 200 megahertz. I did the math, but the wavelengths are 1.5 meters to 10 meters. Yeah, 1.5 to 10 meters. So quarter wavelengths are a quarter of each of those. So we'll call it half a meter to about 2 to 3 meters. Basically, right on par with the dimensions of certainly of this chamber, kind of any typical EMI chamber. Just the biconical antenna is gonna be operating in wavelength ranges comparable to the dimensions of your room. So constructive, destructive interferences are going to be very likely. So that just adds to the complications of testing with the bicon. And as I mentioned last week, I think it's in one of the charts here, it's very inefficient at low frequencies. The VSWR, voltage standing wave ratio, is terrible at the low frequency ranges. So there's just a big, and I think that compounded the problem at this unnamed facility, because I think it was right as we were just trying to get the test started at 30 megahertz. Because of it's very inefficient, because of the high VSWR, you need a lot more power to overcome those inefficiencies to get the desired field level. So we're already applying a fair amount of power, and then what was reflecting off the back wall and coming back in was producing a lot of reverse power that the amplifier didn't like. So, does anybody have any questions or discussion points or war stories of your own that you would like to share?
Hey, John, this is Mike Garrett at Glenn. I know
Hi, Mike.
Hi. I know you have some IFI amplifiers, and we've had some problem. We've had an amplifier we've had for almost 20 years. Had some issues with it and needed to get it serviced. I was wondering if you've had any issues with yours, and if so, how did you get them serviced?
Well,
Greg is smiling.
Yeah, we're in the same boat. We did have some amplifiers go bad, and unfortunately, IFI does not exist. They've been taken over by Ametek, I believe. And so the little support that they can provide is based on the personnel they may have that knows about these amplifiers. So most of the time, if we are basically, we lose one of our amplifiers that is not part of the critical 200 megahertz to 18 gigahertz, then we might not be able to get that replaced. So yeah, as far as repair, since IFI went out, we didn't have to send one for repair. But yeah, if we do, we may have to be required to buy a new one at this point. I mean, most of our amplifiers are more than 10 years, maybe even 20 years. So they won't even service those. So yeah, that's unfortunately it's a time to upgrade. If it's an old amplifier, it gets bad, and there's nobody to repair it. Yeah, we're kind of in the same boat.
What was the nature of the problem you were having? I mean, did it just crap out and just not work, or was there something more subtle?
For us, it was it started putting out a lot of noise at the rail when we weren't even driving it. I did find a former employee of IFI who had started was working for another company. I can't call the name right now. I was trying to look it up on my computer while you were talking, but it turned out to be a cable that had RF cable inside the amplifier that had been damaged. So it was a relatively simple repair, but it took months to find that one guy who had any experience with that amplifier. As a matter of fact, so that's what we had.
That's unfortunate that that company is no longer there. because our lab is pretty much was almost 100% IFI lab. We have some Milmiga amplifiers, but mostly IFI. So yeah, I'm not quite sure what's going to happen if we have a you know, something break. We may have to get it replaced.
One
Copy that.
another thing I just thought of, wanted to mention is, you know, we learned in an interesting way. I'd say so much the hard way, but in an interesting way, these TWT amplifiers put out a lot of broadband noise, and I think by and large you don't care, right? You're deliberately applying a high power RF signal, right? I mean, the higher field intensity that you're trying to apply, like 20 volts per meter, is going to be so much above that noise floor that it doesn't really matter. That's not dominating what you're applying to the EUT. But we had at another unnamed facility that this was also about 10 years ago ish. So we're doing a radiated susceptibility test on an integrated spacecraft, and the part of what we as far as the the RF comm system was concerned, we want to verify we were maintaining lock on the signal. It turned out we didn't really have to do that. So actually, they were to provide the signal, right? Oh, I'm getting a note that I'm dropping out. Can everyone still hear me?
Yeah, but it's choppy.
Connection is a little weak.
Okay.
Maybe
All right,
open the
well-
chamber door again.
We're hardwired.
Yeah, it's a hard line connection now. All right, well, I'll tell this story and then this is about the last thing I wanted to say. So, anyway, they were running a hard line connection to their transponder for the simulated uplink signal, but their antennas, the antennas on the spacecraft were still, I keep looking at my screen here. You guys are over here. The antennas on the spacecraft were still open to, you know, the environment, especially the signal we were applying. And when we got ready to start the test, and this is a full up spacecraft level test, the room is completely full. And this was a Sunday morning, by the way. Whenever I've asked what day do you think some really, you know, horrible, oh my God, what's going on kind of thing could happen, when I've asked what day of the week do you think that was, everybody's first answer is Friday afternoon, which is a pretty good guess, but it was a Sunday morning. I mean, we're testing on a weekend, you know, with fully populated control room. People are, you know, in there on the weekend to do this test because schedule is always paramount at that stage, right? So Sunday morning, room full of people, and I'm the test director basically, right? This test was my baby, and we get go from everyone to proceed. All right, everybody on console is ready to go. They're looking at telemetry and they're ready to establish whether any of their equipment is showing a susceptibility to this applied signal, and tell the EMI guys, basically their equivalent of this crack team here, like, all right, turn on the amplifiers and let's go. As soon as they turned on their tweeter driving the test antenna, we lost our uplink signal, which was, it's a hard line signal, right? How did we lose a hard line signal? Well, it turned out, and this is what we were scrambling for a couple hours to try to figure out what happened, but basically our test antenna was pointing right at one of the Omni antennas on the spacecraft, that even though we were applying a hard line signal to the transponder, the antenna was still open to the environment, to the energy we were blasting right at it, and it was still being summed into the signal chain and going to the transponder. And the calculations we did after the fact, that I think the level that we were hitting it with, the level it was getting to the transponder was something like 70 dB higher than our simulated uplink signal. So we're like, okay, yeah, that's going to kind of dwarf that out, and that explains that. Fortunately, the level was, I don't know, we were a good 20 dB down from the damage threshold, something like that. We're significantly down from the damage threshold that we didn't break anything, and we got lucky there. But the point is that just by turning on the amplifier, they hadn't even turned on the signal generator, or at least signal generator might have been on, but with the RF disabled. But just turning on the amplifier, the TWT amplifier that was connected to the antenna, that broadband noise was enough to just basically blast out of the antenna and hit the Omni antenna on the spacecraft to receive enough RF energy to just completely dwarf out our simulated uplink signal. That was a very interesting day. But once we figured out what happened, that we didn't damage anything, and we were able to eliminate maintaining that uplink signal, or maintaining lock on the uplink signal as a success criteria for the test, we were able to just get on with it and finish the test that day. A few hours later than we initially thought, but we got it done. And I bring up a very non-technical part of that. Before that test, I went to my management and got her. This is the kind of, imparting this sort of thing that, if you're ever in that position to be a test director for a major test like this. I went to my management here at Goddard weeks before the test, maybe even a couple months before the test. And I related my experience that there is always one moment like that, this hands up in the air, what the F is going on. I'm behaving myself and just saying F today. I'm not sure why, but it's not because I'm about to retire, because then I don't care. But anyway, there's always one of these, moments in a test where things can run up the food chain very quickly. And so I said to my management that, I appealed to them to basically designate me as the on-site rep for Goddard Space Flight Center and NASA and the US government to empower me to make real-time decisions as needed. If it's something that, requires customer buy-in, because we get that all the time, we're going to need buy-in from the customer on this. And so I said, it seems like you guys are probably going to come to me for any disposition on that. Anyway, if I'm going to be there on site supporting the test, directing the test, why don't you just basically deputize me to make those decisions in real time as needed to keep the test moving? And if there is something that I really, if I don't feel like it's in my purview to make that decision single-handedly, I will certainly contact you. But if it's a technical issue that I feel qualified to make the decision on, please just give me that authority to make those decisions in real time. And they, without hesitation, they said yes. And I did ask them to put it in writing and send that to the management of this particular contractor. And I've done that for a couple of other test campaigns that I've supported at remote sites. And it's always been very beneficial, because it was a Sunday morning, everybody was sitting on console, probably 24 people or more in the control room. If we had to shut down the test for the day, that it would have been non-trivial. It wasn't a guarantee we could get everybody back in there the very next day, right? It might have been a couple-day hit before we could actually have another go at this test. Once we determined what the problem was, and we realized that really a key point here was that in operation, there was no need to maintain lock on that uplink signal to the transponder during this test. We were simulating the environment during launch. I mean, it was a spacecraft level test. So this wasn't an on-orbit test. This was a launch sequence test. We were simulating radiation susceptibility at the launch site. So it was the launch environment. And we were not going to be required to lock on an uplink signal until 30 some seconds after separation from the launch vehicle. When we were sorting through all of this in real time to disposition what happened and how to proceed, you know, it was very clear that maintaining lock on that uplink signal did not make any sense to be a success criteria for that test, but it was in the requirements that it had to be. The RF guys at the facility were saying, well, we get that technically, but it's in the requirements that's what we should have been doing. That's what we should be doing. So it became a decision that needed to be made by the customer to say that it is okay to redline that out as a success criteria for the test so that we could get on with testing the rest of the spacecraft. We wanted to determine, is there anything in the rest of the spacecraft that is susceptible to this radiated susceptibility energy that we are hitting the spacecraft with? So so that was a big lesson learned there. I already, I had prepared for it by asking management to empower me to be able to make those real-time decisions. But it really paid off, because that would have been a non-trivial hit. If it was something that they were, this was a Sunday, right? So it probably would have been Monday, or, we probably, at this point, people were on call. We probably would have been able to get an FRB together for later in the day or something. It would have been a lot more messy, right? As it was, we were able to have everyone in the room agree that this was the right thing to do. I gave the authorization to proceed with the test. Then I called my management to fill them in on what just happened and basically and just tell them what happened, as opposed to asking for permission to, for whatever needed to be done, and basically just have everyone come to a screaming halt. So either they'd be sitting there for hours while we made a decision, or we send them home and try to start the test on another day. Anyway, just a non-technical lesson learned there to impart that, don't be afraid to ask for that kind of authority. If you're the one in charge of a test, make sure it's clear to everyone involved that you are, and have your management basically deputize you to be able to make those kinds of decisions in real time, because it's pretty likely that something like that is going to occur on a test like that. Anybody else have any questions or comments, discussion points? Okay, well, thank you all for participating. I hope this was worthwhile, and we'll talk to you soon.
Very
Thanks a lot, John.
worthwhile, John. Thanks.
Done.